Our entire galaxy is rushing toward a hidden point in space. This is not a gentle drift, but a headlong fall, moving over 600 kilometers every single second. The force behind this motion is not a push from behind. It is a colossal, invisible pull from a region of space we have never truly seen. This cosmic mystery is known as the Great Attractor. By the end of this journey, you will understand the invisible architecture of our universe and our place within its flowing currents. What unseen mass could possibly command such power, and will our galaxy ever reach its destination? What does it feel like to discover you are not at the center of everything, but are instead caught in a river of stars? The universe's oldest light holds a secret about our motion. In the 1970s and 80s, astronomers trained their instruments on a faint, uniform glow that fills every corner of the cosmos, the cosmic microwave background. This is the cooled remnant of the universe's very first light, a baby picture of the cosmos when it was just 380,000 years old. By studying this ancient radiation, scientists could determine our solar system's absolute rest frame, the backdrop against which all true motion in the universe is measured. What they found was anything but restful. The map revealed a distinct pattern, a dipole anisotropy. In simpler terms, the light appeared very slightly warmer or blue-shifted in one direction of the sky and cooler or red-shifted in the exact opposite direction. This was not a mistake. It was the unmistakable fingerprint of our galaxy's high-speed journey. The entire Milky Way, along with our local group of galaxies, was racing through space. The direction of the warmth pointed toward our destination. The cold spot behind us marked where we had come from. The sheer speed of this motion was the real shock. Calculations showed we were moving at over 600 kilometers per second. Known gravitational sources, like the immense Virgo cluster of galaxies relatively nearby, could only account for a fraction of that velocity. The numbers did not add up. There was a massive deficit in the gravitational ledger. Some immense, unseen concentration of mass far beyond the Virgo cluster was exerting a pull we could not yet see. This velocity anomaly was the first undeniable clue that our cosmic neighborhood was not what it seemed, that our maps of the heavens were profoundly incomplete, hiding a gravitational titan just out of sight. This hidden gravitational titan was given a name that captured its mystery and its power, the Great Attractor. But this name can be misleading. It is not a single, colossal object like a supermassive black hole, though such things may exist within it. Instead, think of the Great Attractor as a gravitational focal point, a region of space where the cosmic architecture has gathered an extraordinary concentration of mass. It lies roughly 150 to 250 million light-years away from us, in the general direction of the constellations Centaurus and Hydra. To visualize it, picture the universe not as a random scattering of galaxies, but as a vast, three-dimensional web. Galaxies cluster along the filaments of this cosmic web, drawn together by gravity over billions of years. The Great Attractor represents one of the densest knots in this web, a grand central station for galactic motion in our corner of the cosmos. Its immense gravity acts like a deep well in the fabric of space-time, and our entire local group of galaxies, including the Milky Way, is sliding down its slopes. Yet for decades, this monumental force remained almost entirely hidden from our view. The reason lies in a cosmic accident of perspective. The direction we must look to study the Great Attractor is directly through the crowded, dusty plain of our own Milky Way galaxy. Astronomers call this the Zone of Avoidance. It is a broad band of gas, dust, and countless stars that form the disk of our galaxy, and it acts like a thick, obscuring curtain. Traditional optical telescopes, which rely on visible light, see mostly a blank, starry wall. The Great Attractor's light from the galaxies that likely compose it is absorbed and scattered by this galactic fog long before it can reach our instruments. So here we have a profound irony. One of the most influential gravitational entities in our local universe, a force dictating the motion of thousands of galaxies, is rendered effectively invisible by our own celestial home. This shroud has turned the Great Attractor from a known destination into one of astronomy's greatest puzzles, a hidden heart of darkness whose true form we have had to piece together through indirect clues and new ways of seeing. For decades, the Great Attractor stood as a mysterious endpoint, a final destination in our galaxy's long fall. But a revolutionary discovery in 2014 changed everything. A team of astronomers led by R. Brent Tully at the University of Hawaii developed a new way to see the invisible. Instead of trying to peer through the zone of avoidance, they decided to watch how galaxies move. They meticulously mapped the velocities of thousands of galaxies in our local universe, tracing the subtle currents and flows of their motion through space. Think of it like watching leaves floating on the surface of a wide, slow-moving river. By tracking the direction and speed of each leaf, you can deduce the shape of the river basin and locate its deepest, most powerful current. This technique revealed not just a single destination, but an entire cosmic watershed. The result was a breathtaking new map of our place in the universe, and it gave us a new name for home, the Laniakea Supercluster. Laniakea, a beautiful Hawaiian word meaning immense heaven, is a fitting title for a structure of almost incomprehensible scale. This is our true galactic continent. It contains over 100,000 galaxies, including our own Milky Way, the Andromeda Galaxy, and the entire Virgo cluster. All of them are bound together by gravity, all flowing along vast filamentary pathways like rivers of stars converging toward the same immense basin. And at the gravitational heart of this continent, at the point where all these cosmic rivers ultimately drain, lies the Great Attractor. This recontextualization was a profound shift in understanding. The Great Attractor is not a lone, distant monster pulling us in. It is the central weight, the core of our local universe. It is the sun around which our galactic metropolis orbits, the deepest well in the valley we all share. Our galaxy's headlong rush is not a journey to a foreign land, but a movement within our own home. We are not falling toward a black hole or a single galaxy. We are flowing with the gentle, inevitable current of an ocean 500 million light years across. This discovery forever changed our cosmic address. We no longer live merely in the Milky Way or even just the local group. We are citizens of Laniakea, a single thread in a tapestry of 100,000 galaxies, all bound by the same invisible pull toward a center we are only beginning to understand. But how can we possibly map something we cannot see? The answer lies not in looking for the object itself, but in reading its influence on everything around it. Astronomers have developed a clever technique to trace this invisible hand by studying the motions of galaxies, focusing on what they call peculiar velocities. Every galaxy we observe has two primary motions. The first is the grand, uniform expansion of the universe itself, often called the Hubble flow. This is the foundational current that carries all galaxies apart from one another over cosmic distances, like dots on an inflating balloon. The second motion is the galaxy's own local drift, its individual journey through the gravitational landscape of the cosmos. This local motion is the peculiar velocity. To find it, scientists perform a kind of cosmic subtraction. They calculate how fast a galaxy should be moving based solely on the universe's expansion and its distance from us. Then they measure its actual, observed velocity. The difference between these two numbers, that extra push or pull, is the peculiar velocity. It is the fingerprint of local gravity. Think of a wide, slow-moving river representing the Hubble flow. Many boats or galaxies simply drift with this current. But if you see a boat steadily moving sideways or even slightly upstream against the current, you know something is unusual. That boat has a peculiar motion. Perhaps a hidden underwater spring is pulling it, or a fisherman is rowing. In the cosmic sense, that peculiar motion reveals the tug of a hidden mass, a gravitational spring like the Great Attractor. By meticulously measuring the peculiar velocities of thousands of galaxies in our region of space, astronomers can essentially work backwards. They watch how the boats are drifting, and from that pattern, they can sketch the shape of the hidden riverbed and locate its deepest point. This painstaking analysis of galactic drift is what first revealed the staggering speed of our own motion and pointed the arrow squarely toward the obscured region we now call home, the heart of Laniakea. So while we can map the river by watching the boats, a more direct question remains: what does the riverbed itself actually look like? To answer that, we needed to find a way to see through the galactic fog. This required a technological leap, a shift from looking with our eyes to listening with our instruments. The dust and gas of the Milky Way's plane, which blocks visible light so completely, is largely transparent to other forms of energy. Infrared light, with its longer wavelengths, can slip between the dust grains. Radio waves pass through almost unimpeded. By building telescopes that see in these invisible parts of the spectrum, we developed a kind of X-ray vision for the cosmos. Missions like NASA's Wide Field Infrared Survey Explorer, or WISE, scanned the entire sky in infrared. Its sensitive detectors could pick up the warm glow of stars and galaxies shining from behind the veil, revealing structures our optical telescopes had missed for a century. On the ground, radio telescopes like the Parkes Observatory in Australia performed a different kind of magic. They tuned in to the faint radio whispers of hydrogen gas, the most abundant element in the universe, which permeates all galaxies. By mapping where this hydrogen signal was strongest, astronomers could trace the outlines of galaxies hiding in the zone of avoidance, even if they could not see their stars directly. This multi-wavelength assault on the cosmic curtain has been spectacularly successful. It has peeled back the obscuring layers to reveal a bustling metropolis of galaxies right in the direction of the Great Attractor. One of the most significant discoveries is the Norma Cluster, a massive gathering of hundreds of galaxies located almost exactly at the predicted gravitational center. This cluster is now understood to be a core component of the Great Attractor, a dense knot of mass helping to generate the profound gravitational well that pulls us in. Seeing these hidden galaxies for the first time was like turning on the lights in a room we had only ever heard echoes from. We are no longer just inferring the giant's presence from its footsteps. We are starting to see the outline of its colossal form, piece by piece, emerging from the shadows of our own galactic backyard. The Norma Cluster is one of the most important discoveries made by peering through the galactic curtain. Located roughly 220 million light-years away, it sits almost perfectly aligned with the gravitational heart we have been pulled toward for eons. This is not a loose gathering of galaxies. It is a true metropolis, one of the richest and most densely packed clusters known in our entire local universe. Hundreds of large galaxies swarm within a relatively small volume of space, all bound together in a ferocious gravitational dance. To grasp its scale, consider that its total mass is equivalent to many thousands of galaxies like our own Milky Way. It is a colossal knot in the cosmic web, a gravitational anchor of almost unimaginable strength. This discovery was a major breakthrough, finally giving a visible face to a force we had only felt. For a moment, it seemed the mystery of the Great Attractor was solved. We had found the giant, yet when astronomers ran the numbers, a new puzzle emerged. The gravitational pull generated by the Norma Cluster and all the other galaxies we have now found in that region, while immense, still does not add up. It accounts for only a fraction of the total force required to explain the 600 km/s rush of our local group of galaxies. The math leaves a staggering gap. There is still an enormous amount of mass influencing that region of space that we simply cannot see with any telescope in any wavelength of light. This points toward a deeper, more pervasive mystery woven into the fabric of the cosmos itself: dark matter. The Great Attractor, therefore, is likely not just a collection of visible galaxies. It may be the core of a supermassive dark matter halo, an invisible scaffolding upon which the visible universe is built. The Norma Cluster is a brilliant, shining city at the center of this darkness, but it is merely the visible tip of a much larger, much darker iceberg whose full dimensions we are only beginning to map. This invisible mass deficit points toward a deeper truth about the cosmos. The universe is built on a hidden framework, a vast and unseen scaffolding that holds everything together. This mysterious substance is known as dark matter. It does not emit, absorb, or reflect any form of light we can detect. It is completely transparent, yet it possesses mass and therefore exerts a powerful gravitational pull. Think of the visible universe, all the stars and galaxies we see through our telescopes, as mere Christmas lights strung along a massive, invisible tree. The lights are beautiful and show us the shape of the branches, but they represent only a tiny fraction of the actual structure. The tree itself, the strong and intricate framework, is the dark matter. In the case of the Great Attractor, the galaxies like the Norma Cluster are those brilliant lights. They are stunning and dense, but their collective gravity is simply not enough to explain the immense river of motion we are caught in. The math demands something more, something far greater. Scientists now believe the heart of Laniakea is not just a cluster of galaxies, but the core of an unimaginably large halo of dark matter. This invisible ocean of mass provides the extra gravitational glue, creating a well in space-time so deep that it commands the motion of our entire supercluster. This realization transforms the mystery. The Great Attractor is not merely hidden behind a curtain of cosmic dust. It is fundamentally constructed from a material we cannot perceive directly. It is a cosmic phantom felt only by its relentless gravitational hand. We are not just falling toward a place we struggle to see. We are being drawn into the heart of a shadow, a testament to the fact that most of the universe's substance is utterly unknown to us. Yet this gravitational landscape is not shaped by attraction alone. Our high-speed journey through the cosmos is a story of two forces, not one. While the Great Attractor pulls us in from one direction, astronomers now believe an equally powerful influence pushes us from the opposite side. This counterpoint is known as the Dipole Repeller. The name itself is a clue, dipole meaning two poles, repeller meaning it pushes away. Recent mapping of the universe's large-scale structure has revealed something astonishing about the region of space directly behind our local group's motion. It is not just empty, it is profoundly empty. This area is a cosmic void, an immense bubble in the universe's web where galaxies are few and far between, where the density of both visible matter and dark matter is exceptionally low. Think of the cosmic web not as a flat tapestry, but as a dynamic, three-dimensional landscape with towering mountain ranges of galaxy clusters and deep, expansive valleys of near-nothingness. The Great Attractor is one of the tallest mountains, the Dipole Repeller is one of the deepest valleys, and in this cosmic terrain, emptiness has its own surprising power. Within a dense region like a supercluster, gravity is the dominant force pulling galaxies together. But within a vast void, a different aspect of the universe's physics takes over, the relentless force of cosmic expansion. The space inside a void, with so little gravitational pull to counteract it, expands a bit faster than the space in denser regions. This does not create an anti-gravity force, but the effect from our perspective is similar. As the void expands, galaxies on its edges are effectively pushed outward, away from the center of emptiness, like driftwood being carried away from a receding tide. So our motion is a cosmic balancing act. We are being sucked toward the immense gravitational well of the Great Attractor and simultaneously shoved away from the expanding emptiness of the Dipole Repeller. This reframes our entire journey. We are not simply falling, we are surfing. We are riding the slope between a mountain and a valley, caught in the dynamic interplay of density and emptiness on the grandest possible scale. Our place in the universe is defined not just by where we are going, but also by what we are leaving behind. But the cosmic river we are surfing does not end at the border of Laniakea. Our entire supercluster, with the Great Attractor at its heart, is itself in motion. All that mass, over 100,000 galaxies flowing together, is being pulled by something even greater. Astronomers have traced this larger current to a structure so immense it makes our home supercluster seem like a local neighborhood. This is the Shapley Supercluster, the single largest concentration of matter in our observable universe. It lies an almost incomprehensible 650 million light-years away in the direction of the constellation Centaurus. To grasp this scale, if the Great Attractor is a major city, Shapley is the entire continent. Its gravitational influence is the ultimate source of the river we find ourselves in. This reveals a profound hierarchy in the architecture of the cosmos. Individual galaxies are drawn into groups and clusters. Those clusters stream along filaments into the gravitational basins of attractors like the one at the heart of Laniakea. And now we see that these superclusters themselves are not static islands, but are also in transit, flowing toward the most massive nodes in the cosmic web. It is a gravitational Russian nesting doll, each layer contained within a larger, more powerful pull. The Great Attractor, then, is not our final destination. It is a colossal waypoint, a major interchange in an interstate system of gravity that spans billions of light-years. Our galaxy's journey is far longer and more winding than we first realized. We are not merely falling toward a hidden center, we are riding a current within a current, caught in a cascade of motion that begins in our local group and ends in the deepest gravitational well our instruments can detect. This reshapes the entire narrative. The force dragging our galaxy is not a single mystery, but a chain of them, each link more powerful than the last, leading our gaze toward a distant, crowded region of space that holds the title of the universe's greatest gathering. This cosmic cascade of motion has a direct and profound impact on our most fundamental measurement of the universe itself, the Hubble constant. This number represents the rate at which the cosmos is expanding, the master clock that tells us the universe's age, its size, and hints at its ultimate fate. To measure it, astronomers look at distant galaxies, measure how fast they are moving away from us, and plot that against their distance. The slope of that line is the Hubble constant. But there is a critical complication, one we have now spent this entire journey exploring. The galaxies we use as markers are not just passively riding the wave of cosmic expansion. They are also caught in their own local currents, their own peculiar velocities, generated by the gravitational pull of structures like the Great Attractor and the push from voids like the Dipole Repeller. These motions are the cosmic equivalent of background noise, a static hiss overlaid on the pure signal of the universe's expansion. If we mistake a galaxy's local drift for the Hubble flow, our measurement becomes distorted. It is like trying to measure the steady flow of a wide river by watching a boat that is also being rowed vigorously by its captain. Your reading of the river's speed will be completely wrong. This is the immense challenge cosmologists face. To hear the true heartbeat of the expanding universe, they must first filter out the gravitational noise of everything in it, the rushing of all the rivers within the river. The Great Attractor and the entire Laniakea Supercluster represents one of the loudest sources of that noise in our local cosmic neighborhood. Until we can accurately map its full mass and influence, a component of uncertainty remains in our most crucial cosmic measurement. This uncertainty is not just a minor detail, it has blossomed into a major tension in modern cosmology. Different methods of measuring the Hubble constant, some looking at the very early universe and others at more recent expansion, have begun to yield stubbornly different results. While the cause of this Hubble tension is still debated, one leading candidate is that we have not fully accounted for all the large-scale flows, the tug of hidden attractors and the push of vast repellers that distort our local view. Solving the mystery of the Great Attractor, therefore, transcends a curiosity about our own galactic journey. It becomes an essential step in calibrating the ruler we use to measure everything. By understanding this invisible force dragging our galaxy, we are not just learning where we are going, we are cleaning the lens through which we see the entire history and destiny of the cosmos. Our galaxy's journey is set on a course measured in billions of years. Given our current velocity of over 600 kilometers per second, the Milky Way and our entire local group of galaxies will continue this immense fall toward the gravitational heart of Laniakea for eons to come. We are locked into this cosmic river destined to draw ever closer to the Great Attractor. Yet this raises a profound question about our ultimate destination. Will we ever actually arrive? The answer introduces a new and dominant character in the story of the universe, one that works in direct opposition to the pull of gravity. This force is dark energy. Observations over the past few decades have revealed that the expansion of the universe is not slowing down, as one might expect from the tug of all its matter. It is speeding up. Something is causing space itself to stretch at an ever-increasing rate, and we call this mysterious influence dark energy. On the grandest scales, dark energy acts as a kind of cosmic repulsion, a counterforce to gravity's relentless pull. While gravity draws matter together locally, creating clusters and superclusters, dark energy works globally, pushing the vast voids between these structures to expand even faster. This sets up a fundamental tension for our long-term future. As we flow toward the Great Attractor, the very fabric of space across the immense distance between us is also being stretched. Think of it as trying to walk up a down escalator that is gradually increasing its speed. You are moving forward, but the ground beneath you is moving backward even faster. For billions of years, gravity will win this local tug of war. We will continue to approach the core of our supercluster. But as the universe ages and dark energy's influence grows, the escalator's speed may eventually match and then exceed our own progress. The gravitational bonds that hold superclusters like Laniakea together are not unbreakable. Over timescales so vast they defy human imagination, dark energy could cause these immense structures to stretch, thin, and ultimately dissolve. The individual filaments of the cosmic web would drift apart, isolating galaxy clusters in a sea of ever-growing emptiness. This leads to a poignant and almost poetic cosmic paradox. Our galaxy's fate may be an eternal fall toward a destination we can never truly reach. We are drawn forever toward a center that, because of the accelerating expansion of space itself, remains perpetually over the horizon. The Great Attractor, the invisible force that has dictated our motion for billions of years, may ultimately become a receding landmark, a gravitational siren song fading into the void. Our journey, then, is not about arrival. It is about the flow itself, a testament to the dynamic and opposing forces that shape the universe from its smallest structures to its grandest fate. Mapping this grand gravitational watershed demands a view we still cannot fully achieve. The Zone of Avoidance, that thick band of our own galaxy's dust and stars, continues to be the ultimate blind spot in our cosmic map. While infrared and radio surveys have peeled back the curtain to reveal wonders like the Norma Cluster, we are still looking through a dense, hazy fog. We see shadows and outlines, but not the complete, detailed picture. To truly understand the Great Attractor, we need more than glimpses. We need a complete census of every galaxy in that region, a precise measurement of their distances and motions, to build a definitive three-dimensional map of the mass that pulls us. This is an immense observational challenge, requiring us to survey vast areas of the sky with incredible sensitivity, to see the faintest galaxies hiding in the dust. The task is like trying to map an entire mountain range while standing in a deep valley filled with mist. You can see the peaks of the closest mountains, but the full scope and connection of the entire range remains hidden. For decades, this has been the frustrating limit of our knowledge. We know the river's current is powerful, we have found some of its major sources, but the complete topography of its basin eludes us. This is about to change. A new generation of astronomical observatories designed with these very challenges in mind is poised to revolutionize our view. These are not just incremental improvements, they are leaps in capability that will transform the shadowy outline of the Great Attractor into a sharply focused portrait. The key lies in two ambitious projects that will scan the heavens in ways never before possible. The Vera C. Rubin Observatory, currently under construction in Chile, will house the legacy survey of space and time. This is an endeavor of almost unimaginable scale. Over 10 years, its enormous mirror and giant camera will image the entire southern sky every few nights, creating the deepest, widest movie of the universe ever made. It will detect billions of galaxies, and crucially, it will do so in optical and near-infrared light. This infrared vision is our tool to peer through the galactic dust. The survey is expected to find millions of new galaxies currently hidden within the Zone of Avoidance, finally filling in the blank spots on our map of the local universe. Across the ocean, the European Space Agency's Euclid telescope, now in space, has a complementary and equally profound mission. Euclid is designed to map the geometry of the dark universe. It will observe billions of galaxies to measure the subtle distortions caused by dark matter, creating the most extensive chart of the invisible cosmic web ever assembled. Together, these instruments will provide something we have never had: a complete mass inventory of our region of space. By combining Rubin's census of visible galaxies with Euclid's map of the dark matter scaffolding, we will finally be able to weigh the Great Attractor with precision. We will see not just the glittering cities of stars like the Norma Cluster, but the full extent of the dark matter continent they rest upon. This data will allow us to run the gravitational equations to their final conclusion, to see if the combined pull of all this visible and invisible mass finally accounts for our relentless 600 km/s motion. The answers are written in the light of millions of unseen galaxies, and for the first time we are building the eyes to read them. Gravitational lensing offers a way to weigh the invisible directly. This phenomenon is one of the most elegant predictions of Einstein's theory of general relativity. It states that mass warps the very fabric of space and time, and light traveling through this warped space must follow the curves. A massive object like a galaxy cluster acts as a lens in space, bending the light from more distant galaxies that happen to lie directly behind it from our point of view. The effect can be dramatic, creating multiple images of a single quasar or stretching a galaxy's light into a brilliant, luminous arc. But for mapping something like the Great Attractor, astronomers rely on a far more subtle signature: weak gravitational lensing. Instead of creating obvious arcs and rings, the immense mass of the foreground region distorts the shapes of thousands upon thousands of faint background galaxies in a specific, statistical way. Each individual galaxy's distortion is minuscule, almost imperceptible, but by analyzing the collective, coherent warping across a vast field of view, scientists can perform a kind of cosmic tomography. They can reconstruct the total mass distribution in the foreground, the lumpy landscape of gravity that caused the light to bend. The true power of this technique is its blindness to the nature of the mass. It does not care if the gravity comes from brilliant stars, hot clouds of X-ray emitting gas, or the silent, invisible presence of dark matter. It measures the sum total of all gravitational influence. For the Great Attractor, this is the ultimate tool. By pointing the Vera C. Rubin Observatory and the Euclid telescope toward the obscured region in Centaurus and Hydra, they will capture the shapes of millions of background galaxies seen through that part of the sky. The resulting weak lensing map will be a direct image of the gravitational well itself. It will show the depth and shape of the basin we are falling into, revealing the full architecture of the attractor in a way light alone never could. This is not looking for the hidden cities, but mapping the entire mountain range by the way it bends the horizon behind it. The data will give us a number, a precise measurement of the total mass pulling on our galaxy. It will finally answer the lingering question, does the combined weight of everything we can now see and map account for our motion, or does an even deeper layer of mystery remain? The profound mystery of the Great Attractor has made it a natural star in the stories we tell ourselves about the cosmos. In science fiction, where the unknown becomes a canvas for human hopes and fears, this invisible force has been reimagined in countless ways. It often appears not as a cluster of galaxies, but as a singular, almost mythical destination, a place of ultimate revelation or unimaginable power. In novels and films, journeys toward the Great Attractor become grand odysseys, framing it as a cosmic finish line or a source of transcendent knowledge that could change civilization forever. Video games transform it into a region of space brimming with ancient alien technology or perilous gravitational anomalies, a final frontier for the player to navigate. These fictional portrayals rarely concern themselves with the precise astrophysics of dark matter halos. Instead, they tap into the core emotional truth the concept evokes, a powerful, invisible pull toward something monumental and unknown. This cultural reflection reveals something fundamental about us. When science presents a gap in the map, when it points to a force we can measure but not see, storytelling rushes in to fill the void. The Great Attractor becomes more than a gravitational anomaly. It becomes a symbol. It represents the eternal human drive to explore, the quest for a center, and the haunting question of whether our journey through the universe has a predetermined destination. This artistic fascination underscores that the allure of this cosmic mystery is not merely intellectual. It is deeply, profoundly human. It speaks to our innate desire to find meaning in the void, to look toward a hidden horizon and imagine what wonders or what truths might lie in waiting. The stories we spin around it are, in their own way, another method of mapping the unknown, using the tools of narrative to grapple with the same awe that the raw scientific data inspires. This journey through the cosmic web forces a profound shift in perspective. For most of human history, we placed ourselves at the absolute center of everything. The Earth stood still and the heavens revolved around us in a perfect, ordered celestial sphere. That was the first great illusion to shatter. We learned our world is not the center, but a planet orbiting a star. That was a monumental demotion. Then came the second realization that our sun is not the center either, but one of hundreds of billions of stars in a spinning disk we call the Milky Way. Our position shifted again from the heart of a solar system to a quiet suburb in a vast galactic city, and now we confront this third and perhaps most humbling truth. Our entire galaxy, that breathtaking swirl of light containing every star we have ever seen, is not a fixed island in the void. It is a single leaf caught in a river of other leaves, all flowing together toward a gravitational horizon we cannot see. We are passengers on a vessel in perpetual motion with no fixed anchor in the cosmos. This could easily be framed as a story of insignificance, a crushing reminder of our smallness. But that interpretation misses the deeper, more beautiful truth revealed by this endless recentering. Each time we are moved from the center, we are not being cast adrift. We are being connected, we are being woven into a larger story. To know that our local group of galaxies is bound by gravity is to understand we have neighbors. To discover we are part of the Laniakea Supercluster is to learn we belong to a continent. To feel the pull of the Great Attractor is to know we are participants in a dynamic, flowing architecture that spans hundreds of millions of light years. Our motion is not random drift, it is a signature of our membership in something vast. This transforms our cosmic address from a point of lonely privilege to a node in an immense network. We are not at the center, but we are of the center, in the sense that the forces shaping the greatest structures also shape our path. The same gravity that draws mountain streams into rivers and rivers into oceans is drawing our galaxy into a current that will flow for billions of years. This is not a lesson in isolation, but in profound and fundamental belonging. We are integral threads in the grand tapestry of space-time, our destiny forever intertwined with the invisible architecture of the universe itself. Our journey has no final destination because we are already home, riding the currents of a cosmos that is alive with motion. The architecture we find ourselves in is not a singular masterpiece. If we could step back and view the universe from a truly external vantage point, a breathtaking pattern would emerge. The Great Attractor, for all its profound influence on our local group of galaxies, is almost certainly not unique. It is a single example of a universal phenomenon, a gravitational focal point that emerges naturally wherever matter gathers under the relentless influence of gravity. Across the observable universe, in other superclusters far beyond the borders of Laniakea, similar immense concentrations of mass are likely at work. These distant attractors serve as the hearts of their own galactic continents, orchestrating the motion of thousands of galaxies in their own vast, swirling dances. This realization is both humbling and illuminating. Our headlong rush toward the obscured center of Laniakea is not a special or chosen path. It is simply how gravity structures the cosmos on the grandest scales. Every galaxy in some distant supercluster is likely caught in a similar current, flowing toward its own local center of gravity. This perspective normalizes our experience. We are not falling toward a cosmic anomaly, we are participating in a universal rule. The pattern reveals a fractal-like quality to the universe's design. From the smallest scales, where dust grains clump to form planets, to the immense scales of superclusters, the same principle repeats. Gravity draws matter together, forming clusters, and those clusters are drawn toward larger gatherings, creating a hierarchy of attraction that spans the entirety of cosmic space. Our attractor is special to us because it is our home, the central weight of our immediate universe. But in the grand catalogue of the cosmos, it is one of many, a common feature in an endless tapestry of gravitational basins. This is a powerful testament to the universality of physical law. The same gravity that causes an apple to fall from a tree on Earth, scaled up by almost unimaginable factors of mass and distance, is what gathers hundreds of thousands of galaxies into a supercluster and sets them in motion toward a common center. The force is identical, only the stage has changed. So while we map the specific contours of our own hidden giant, we can now understand it as part of a much broader cosmic chorus, where every major structure sings the same gravitational song, each from its own corner of the dark. Our story of mass has so far focused on the darkness and the light, on invisible halos and brilliant galaxies. But there is another form of matter in this cosmic equation, one that fills the vast spaces in between. Within the crowded metropolis of a galaxy cluster like Norma, the space between the galaxies is not empty. It is filled with a searingly hot, incredibly thin gas known as the intracluster medium. This plasma is so hot, tens of millions of degrees hot, that it does not shine in visible light. Instead, it glows in the high-energy realm of X-rays. To see it, we need the eyes of space telescopes like NASA Chandra X-ray Observatory. When Chandra looks toward the heart of the Great Attractor, it does not see darkness or pinpricks of starlight. It sees a faint, diffuse, luminous fog. This fog is the ghostly outline of the cluster itself, a map of its atmosphere. The discovery of this hot gas was a revelation. For decades, when we added up the mass of all the stars in all the galaxies of a cluster, the numbers fell desperately short of the gravitational strength needed to hold the cluster together. Something else was providing the binding glue. A major part of that something is this intracluster medium. In fact, in many massive clusters, the total weight of this superheated gas can exceed the combined weight of every single star in every single galaxy. It is the dominant form of normal or baryonic matter in these colossal structures. This is a profound correction to our intuition. When we look at a beautiful image of a galaxy cluster, our eyes are drawn to the glittering cities of stars. But the true bulk of the ordinary matter is the invisible ocean of million-degree plasma in which those cities float. Mapping this hot gas with X-ray telescopes gives astronomers a critical piece of the puzzle. By measuring its temperature, density, and distribution, they can calculate its mass with remarkable precision. This data goes directly into the ledger for the Great Attractor's total baryonic budget. It tells us how much of the gravitational pull we feel can be attributed to normal matter we can, in a sense, see, even if it requires X-ray vision to do so. Yet, even after we account for all the stars and all this scorching intergalactic gas, the ledger still does not balance. The combined pull of all this normal matter is still insufficient. This hot plasma is a vital component, a massive contributor we once missed entirely, but its inclusion only deepens the central mystery. It underscores that the visible universe, in all its forms, is merely the luminous tracer of a far deeper and darker reality. The persistent gap in our gravitational ledger invites a bold question. Could the force we are feeling be something other than hidden mass? Could it instead point to a subtle flaw in our understanding of gravity itself? This is the provocative premise of theories like modified Newtonian dynamics, or MUND. Proposed in the 1980s, MUND suggests that on the vast, diffuse scales of galaxies and galaxy clusters, gravity behaves differently than Isaac Newton or Albert Einstein predicted. Instead of requiring immense halos of invisible dark matter to explain the rapid orbits of stars in galaxies, MUND proposes a simple modification to the equations of motion at extremely low accelerations. In this view, the apparent extra pull of the Great Attractor might not be due to a mountain of dark matter at all, but could be a signature of gravity's true nature on cosmic scales, a gentle strengthening of its grip where its pull is weakest. While MUND has had some success explaining rotation curves of individual galaxies without dark matter, it struggles to account for all the evidence from galaxy clusters and the large-scale structure of the universe that strongly supports the existence of dark matter. Yet its persistence as a scientific idea highlights a crucial truth. Profound mysteries like the Great Attractor force us to check our assumptions at the most fundamental level. Another, even more exotic possibility lies in the earliest moments of creation. Some theoretical physicists have proposed that the immense flows we observe could be influenced not by matter, but by scars in the fabric of reality itself. In the searing heat of the Big Bang, as the universe underwent rapid phase transitions, topological defects might have formed. These are stable, persistent irregularities in space-time, like cosmic knots or textures frozen into the expanding cosmos. If such a defect existed in our local universe, its gravitational influence could potentially mimic the pull of a massive overdensity, creating the coherent river of motion we find ourselves in. These ideas are undeniably speculative and remain far outside the scientific mainstream, which overwhelmingly points to a combination of dark matter and normal matter as the explanation. But their very existence on the fringe of cosmology is important. They remind us that the map is not the territory. Our models of the universe, however successful, are approximations of a deeper reality. When we encounter a phenomenon that strains our current understanding, it is not a failure but an invitation. The Great Attractor, by withholding its full secrets behind a veil of dust and darkness, ensures that all serious possibilities, however unconventional, must remain on the table. This intellectual openness is the engine of discovery. It is what drives us to build more powerful telescopes, to devise more clever tests, and to peer ever deeper into the cosmic fog, not just to find an answer, but to ensure we are asking the right questions in the first place. Translating this cosmic cascade into something we can feel and see is an art in itself. Astronomers and science communicators face the beautiful challenge of taking these abstract concepts, these rivers of dark matter and flows of galaxies, and making them tangible for the public. The key lies in building bridges of understanding, using tools that transform data into experience. One of the most powerful methods is the interactive simulation. Imagine sitting at a computer, not just reading about Laniakea, but piloting a virtual spacecraft through it. You can zoom out from the Milky Way, watch our local group of galaxies shrink to a speck, and see the entire filamentary structure of our supercluster emerge around you. You can trace the gravitational currents like glowing highways in the dark, following the path our galaxy will travel for billions of years. These are not mere animations. They are often built directly from the same observational data used in research, turning raw numbers into a navigable cosmos. In planetariums around the world, this experience becomes immersive. Fulldome shows project these visualizations onto a vast, wraparound screen, allowing audiences to feel as if they are flying through the cosmic web itself. The sensation is one of profound reorientation. You are no longer looking up at a static sky. You are moving within a dynamic, three-dimensional architecture. You witness the Great Attractor not as a point on a map, but as the gravitational basin toward which an ocean of galaxies slowly drains. This translation from spreadsheet to spectacle is not just for show. It serves a vital purpose in the scientific ecosystem. By allowing people to viscerally grasp these monumental ideas, we foster a shared sense of wonder and curiosity. This public engagement does more than educate. It builds a foundation of support and inspiration for the scientific endeavor. It reminds us that the quest to understand forces like the Great Attractor is not confined to isolated laboratories. It is a collective human journey, a story we are all a part of, unfolding in the data on a screen and the awe on a viewer's face. When a person leaves a planetarium having flown through the supercluster, they carry with them a new perspective, a silent understanding that our place in the universe is both more humble and more connected than they ever imagined. The story of the Great Attractor is not a single eureka, a moment, but a century-long detective story written in the light of distant galaxies. It began with a fundamental shift in our cosmic perspective, the realization that our universe is expanding. In the 1920s, Edwin Hubble's observations of receding galaxies shattered the idea of a static cosmos and gave us our first real sense of the universe's scale and dynamism. This was the essential foundation, the understanding that galaxies move and that their motions tell a story. For decades, however, the tools to read that story in detail simply did not exist. Measuring galaxy distances was a painstaking, one-by-one process. The cosmic map was a sketch with vast, empty regions. The first clue that our local motion was unusual came in the 1970s with those careful studies of the cosmic microwave background. The discovery of the dipole anisotropy, that telltale warmth in one direction and cold in the other, was the first hard evidence that our entire galactic neighborhood was rushing through space at a startling speed. It was the first measurable tremor of a distant giant's footsteps. The 1980s marked the era of the great redshift surveys. Astronomers like R. Brent Tully, David Burstein, Sandra Faber, and others began systematically measuring the velocities and positions of thousands of galaxies, using new instruments and painstaking observation. It was from this data that the velocity anomaly became undeniable, and the term Great Attractor was coined. They could point to a region of sky and say, something immensely massive is there, pulling us toward the constellations Centaurus and Hydra. Yet the map remained frustratingly two-dimensional, and the Zone of Avoidance kept its secrets. The quest then became a technological arms race against cosmic obscuration. The 1990s and 2000s saw the rise of multi-wavelength astronomy. Space telescopes like the Infrared Astronomical Satellite and later the Wide-Field Infrared Survey Explorer peered in infrared light. Radio telescopes like Parkes in Australia listened for the hydrogen signature of hidden galaxies. The X-ray eyes of the Rosat and Chandra observatories revealed the million-degree atmospheres of massive clusters. Each new wavelength peeled back another layer of the galactic fog, slowly populating the blank spot on our map with the brilliant cities of the Norma Cluster and other massive structures. The pivotal synthesis arrived in 2014. By combining decades of positional data with sophisticated models of cosmic flows, the team led by Brent Tully unveiled the Laniakea Supercluster. This was the moment the riverbed was finally mapped. The Great Attractor was no longer just a mysterious pull. It was identified as the gravitational core of our home continent of galaxies. This paper connected the dots between thousands of individual data points to reveal a single, flowing structure. Today, we stand on the threshold of the next great leap. Projects like the Vera-C, Rubin Observatories' Legacy Survey of Space and Time, and the European Space Agency's Euclid Telescope represent the culmination of this historical progression. They are the direct descendants of those early redshift surveys, but with capabilities those pioneers could only dream of. They promise to complete the census, to weigh the dark matter, and to deliver the precise, three-dimensional mass map that will finally close the gravitational ledger. This timeline is a powerful testament to the nature of science itself. It is a story of incremental progress, where each generation of researchers builds upon the questions and partial answers of the last. It is a narrative driven not by a single genius, but by collective curiosity, technological ingenuity, and the simple, persistent desire to look into the darkness and draw a better map. We are the beneficiaries of a century of patient observation, and soon we may write the final chapter in this particular cosmic mystery. The quest to map the Great Attractor has ignited a quiet revolution far beyond the telescope dome. Today, cosmology is as much a science of bytes and algorithms as it is of light and lenses. The monumental sky surveys now underway, like the Legacy Survey of Space and Time, are not simply taking pictures. They are generating a torrent of data so immense it defies traditional analysis. Every night, these observatories will capture terabytes of information, cataloging billions of galaxies, stars, and transient events. Finding the subtle gravitational signal of the attractor within this ocean of data is like listening for a single, specific whisper in a roaring stadium. This is where modern data science takes the lead. Sophisticated machine learning algorithms are trained to sift through the noise, identifying galaxies, measuring their shapes for weak lensing studies, and classifying objects at a speed and accuracy impossible for human eyes. Supercomputers run complex simulations that model the gravitational dance of millions of galaxies over billions of years, creating virtual universes to test our theories against the observed flows. The Great Attractor has become a premier benchmark problem for big data in science. It demands new computational techniques to handle three-dimensional mapping, statistical analysis of colossal datasets, and the visualization of structures spanning hundreds of millions of light years. The tools developed for this cosmic cartography do not stay confined to astronomy. They ripple outward. The same machine learning models that find hidden galaxies are adapted to spot subtle patterns in medical imaging, aiding in early diagnosis. The data compression algorithms that make cosmic surveys manageable improve how we stream video and store information. The supercomputing architectures built to simulate the universe are used to model climate systems, design new materials, and understand the folding of proteins. This interdisciplinary flow reveals a beautiful truth. The drive to answer a fundamental question about our place in the cosmos does not exist in a vacuum. It catalyzes a wave of innovation that touches countless aspects of our lives. By chasing the invisible force that pulls our galaxy, we are not just mapping dark matter, we are refining the very tools we use to see and understand complexity in our own world. The search for the Great Attractor, therefore, is more than an astronomical endeavor. It is a proving ground for the next generation of discovery, wherever that discovery may need to happen. This cosmic quest for understanding is not confined to scientific papers and data streams. It has spilled over into a vibrant realm of color, sound, and form, where artists and data visualizers translate the invisible flow into works that speak directly to the soul. The very imagery of the Great Attractor and the Laniakea Supercluster, with its delicate filaments of galaxies streaming toward a hidden heart, possesses an inherent, breathtaking beauty. In the hands of visual artists, these cosmic flows are rendered not as dry charts, but as luminous neural networks, sprawling celestial root systems, or rivers of light in an abyssal dark. The resemblance to biological structures is uncanny and deeply moving. It suggests a universal pattern, a common language of connection that repeats from the microscopic networks in our own brains to the largest structures in the observable universe. This visual echo creates an instant, intuitive understanding that bypasses complex equations. We see the map of Laniakea and we recognize it not as an alien diagram, but as a familiar pattern of life and growth written across an impossible scale. This translation extends beyond the visual into the realm of sound. Composers and sonic artists have begun to use the data itself as a score. They assign musical notes to the positions of galaxies, or translate the velocity flows into sweeping, ambient soundscapes. The result is a symphony of the supercluster, where the silent motion of billions of stars becomes a haunting, ethereal melody. Listening to such a piece, one does not learn the exact distance to the Norma Cluster, but one feels the grandeur of the journey. It communicates the emotional weight of the data, the awe and the mystery, in a way a graph simply cannot. This artistic impulse serves a profound and dual purpose. First, it creates objects of sheer beauty, standalone works that celebrate the wonder of the cosmos. But second, and perhaps more importantly, it acts as a vital bridge. It connects the cold, empirical facts of redshift and peculiar velocity to the warm, human experience of wonder. For many, a stunning visualization or a piece of data-driven music is the gateway that sparks the curiosity to learn more about the science behind it. It makes the abstract tangible, the immense personal. In this way, the artistic response to the Great Attractor completes a vital circle of understanding. Science gives us the facts, the measurements, the map of the river. Art gives us a way to feel the current, to stand on the bank and hear its roar. Together, they affirm that wonder is not an unscientific reaction. It is the very fuel of discovery. The artists remind the scientists and all of us that behind every dataset is a story of motion, connection, and a hidden center pulling us forward. They validate our innate desire to not just know the universe, but to feel a part of its flowing, beautiful, and mysterious design. A name is the first story we tell about a discovery. The Great Attractor, as a title, does more than describe, it evokes. It conjures an image of a cosmic siren, a hidden giant whose silent call we cannot resist. This power of naming is not incidental, it is fundamental to how we relate to the cosmos. It transforms raw data into a character in our shared narrative, turning gravitational equations into a destination we can wonder about. But with this power comes a profound responsibility, one that modern astronomy is beginning to embrace with greater intention. When the structure containing our galaxy was finally mapped, the team did not simply assign it a dry catalog number. They sought a name that carried weight, history, and respect. They chose Laniakea from the Hawaiian language, meaning immense heaven or immeasurable sky. This choice was a deliberate homage to the Polynesian navigators who, long before modern instruments, mastered the art of wayfinding across the vast Pacific using the stars, the waves, and the flight of birds. Their celestial knowledge was a science of observation and deep cultural tradition, a way of seeing the sky that was both practical and sacred. To name our galactic continent Laniakea is to weave that legacy directly into the fabric of our cosmic map. It acknowledges that the human impulse to navigate and understand the heavens is a universal story, told in different languages and from different shores. This shift represents a growing awareness within the scientific community. The cosmos does not belong to any single culture, and our maps of it should reflect the rich diversity of human perspective. Names are not just labels, they are invitations. They decide who feels a sense of ownership and belonging in the story of discovery. When we use terms drawn from a wide spectrum of human languages and traditions, we make the universe feel more like a shared home and less like the exclusive territory of a single academic discipline. It is a reminder that the telescope and the voyaging canoe are both instruments of exploration, guided by the same fundamental curiosity. This ethical dimension adds a crucial layer to our pursuit. Charting the invisible currents of dark matter is a technical marvel, but deciding what to call the places we find is a deeply human act. It connects the values we hold here on Earth to the way we conceive of the heavens. As we prepare to fill in the final blanks on our map of the Great Attractor with the next generation of observatories, we are also writing the legend that will accompany it. That legend can be one of inclusive wonder, honoring the many ways humanity has always looked up and found its way. In doing so, we ensure that our cosmic cartography charts not only mass and velocity, but meaning and connection. Our cosmic map, for all its newfound detail, still holds profound questions within its blank spaces. The coming flood of data from observatories like Rubin and Euclid is not about collecting more points on a chart, it is about seeking specific, transformative answers. First and foremost, we hope to finally resolve the gravitational ledger. By combining a complete census of galaxies with a precise weak lensing map, we will be able to weigh the Great Attractor region with an accuracy never before possible. Will the total mass of all the visible galaxies, the Hot Intracluster gas, and the mapped dark matter halo finally equal the force needed to explain our 600 km/s motion? Or will a stubborn discrepancy remain, pointing to an even deeper layer of the unknown, perhaps to the nature of dark matter itself? This precise accounting is the primary goal, to turn a mysterious pull into a quantified and understood feature of our local universe. Beyond balancing the books of our own supercluster, our gaze extends further upstream. We now know Laniakea is flowing toward the Shapley Supercluster. But what lies beyond Shapley? Is it the ultimate destination, or is it, too, caught in a broader current we have yet to perceive? Future surveys that map ever larger volumes of the universe may reveal that these immense concentrations are themselves mere waypoints in a hierarchy of attraction that spans billions of light years. Each new horizon we reach forces us to look for a larger one, a perpetual expansion of our cosmic context. This leads to the most profound temporal question of all, the role of dark energy. Our models suggest that over timescales so vast they defy comprehension, the accelerating expansion of space will eventually overcome local gravity. Will the bonds of Laniakea hold, or will dark energy stretch and dissolve our supercluster, leaving our galaxy adrift in an ever-growing void? Understanding the precise interplay between the attractive force of the Great Attractor and the repulsive force of dark energy is key to forecasting the ultimate fate of our corner of the cosmos. The ultimate ambition is elegant integration. For decades, the Great Attractor has been an anomaly, a puzzling excess velocity that did not fit neatly into our models. The goal of this new era of observation is to fully incorporate it. We aim to transition it from a mysterious headline into a standard paragraph in the textbook of cosmology, a fully explained component of the large-scale structure. Its mass, its influence, and its place in the gravitational cascade will be quantified and fed back into our simulations of the universe, refining our understanding of everything from galaxy formation to the value of the Hubble constant. This process exemplifies the very heart of the scientific endeavor. It is a cycle without end. Each new instrument, each deeper map, provides answers that are immediately satisfying, yet they inevitably reveal new and more subtle questions waiting just beyond the edge of our vision. The story of the Great Attractor teaches us that our universe is not a puzzle to be solved, but a narrative to be continually read. Every revelation is not an ending, but a new beginning, ensuring that our journey of cosmic discovery, like the river of galaxies we ride, flows onward without end. The light reaching our telescopes from the Great Attractor began its journey over 200 million years ago. When that photon first leapt into the void, the continents on Earth were locked together in the vast supercontinent of Pangaea, and the first small dinosaurs were just beginning their long reign. Every human story, every empire that has risen and fallen, every word ever spoken or written, has all unfolded in the time it took for that single beam of light to finally cross the abyss and land in our instruments. This scale is not meant to make our lives feel small or insignificant. It is an invitation to expand our sense of context, to see our moment not as the entirety of existence, but as a single, vivid point in an epic narrative of time and space. Consider the force we have been discussing, that immense gravitational pull. Its influence on our galaxy is not an instantaneous command. It is a slow, patient pressure that has been applied across eons, a gentle steering that operates on timescales far longer than our species has even existed. Our entire recorded history is less than a blink in the duration of this cosmic interaction. Within this vast and flowing architecture, our human experience occupies a sliver of a sliver. Yet here is the profound counterpoint, the detail that turns awe into wonder. Within this fleeting moment, on a tiny world orbiting an ordinary star in the quiet suburbs of a spiral galaxy, a species emerged that can do something extraordinary. We can look out into that deep dark, we can measure the ancient light, we can trace the invisible rivers of gravity and map the continents of the cosmos. We can wonder about forces whose origins predate our planet itself. That ability to ponder, to question, and to seek understanding across such impossible distances is perhaps the most remarkable phenomenon in this entire story. It is a tiny but brilliant spark of conscious light in the grand, dark flow. Our lives are brief against the cosmic clock, but in our capacity to comprehend the clockwork, we find a connection that transcends scale. We are not just passengers on this journey, we are the part of the universe that has awakened to tell its own story. The story of this hidden giant is still being written, and you can be part of the next chapter. The quest to unveil the Great Attractor is a living, collaborative science, and its discoveries are shared with the world in near real time. You can witness them yourself. Begin by visiting the image galleries of space agencies like NASA and the European Space Agency. There, you will find stunning visualizations of the cosmic web, portraits of galaxy clusters like Norma, and the latest data releases that map our flowing universe. For a more hands-on role, explore citizen science platforms like Zooniverse, which often feature projects connected to the Sloan Digital Sky Survey. Here, you can help astronomers classify galaxies, contributing directly to the effort of mapping the large-scale structure that contains mysteries like our attractor. To follow the forefront of this search, turn your attention to the next generation of explorers. Follow the official social media accounts and websites of the Vera C. Rubin Observatory and the Euclid Space Telescope. These are not just instruments, they are the new eyes of humanity, and their teams regularly post first looks, data visualizations, and breakthrough announcements as they scan the sky. You will be among the first to see the hidden galaxies they pull from the Zone of Avoidance, watching the map of our home supercluster come into complete focus. And on a clear, dark night, step outside, find the southern constellations of Centaurus and Hydra. You will not see the attractor, of course. Your view will be a beautiful, starry wall, the luminous disk of our own Milky Way. But now you know the truth behind that veil. In that exact direction, 250 million light-years away, lies the immense gravitational heart of our home continent of galaxies, a cosmic mystery whose final secrets are just now drifting into view. You are looking toward the hidden center of your universe, a reminder that the greatest discoveries are not endings, but invitations to look deeper. The Great Attractor is far more than a scientific puzzle to be solved. It stands as a profound reminder of our true place within a dynamic, interconnected, and still deeply mysterious universe. This journey began with a subtle warmth in the ancient light of creation, a clue that our motion was not our own. It led us through the obscuring veil of our own galaxy to map the immense continent of Laniakea, a home we never knew we had. Each step of this discovery has served to both humble and expand our cosmic perspective, pulling us from an imagined center and weaving us into the grand tapestry of the cosmos. We are not static observers. We are active participants in a gravitational dance set in motion billions of years before our sun first ignited, flowing on currents that will continue long after our star fades. This understanding transforms our relationship with the night sky. It is no longer a distant, silent dome, but a living, flowing architecture of which we are an intrinsic part. The quest to see the unseen, to weigh the invisible, is a testament to a force far more powerful than gravity alone. It is the unquenchable engine of human curiosity. It is what drives us to build telescopes that see in every wavelength, to write algorithms that find patterns in the noise, and to tell stories that make the vastness feel like home. As the next generation of observatories turns its gaze toward the hidden heart of our supercluster, remember that you are part of this ongoing story. Keep looking up with wonder, keep questioning the darkness, share this sense of awe with others, for it is through shared curiosity that we illuminate the unknown together. If this cosmic voyage has reshaped your view of the heavens, consider subscribing for more journeys to the edges of understanding, and we would love to hear from you. What cosmic question pulls at your imagination the most? What hidden force or distant mystery makes you look up and wonder? Let us know in the comments.